Hey, do you know why semiconductor technology is advancing so fast? Today, we'll explore two key principles of semiconductor technology advancement, Moore's law and Huang's law, and their impact on the economy and technological innovation. Moore's law is one of the legendary laws of the semiconductor industry. First proposed by Intel co-founder Gordon Moore in 1965, it states that the number of transistors on a semiconductor chip doubles approximately every 18 to 24 months. It has since become a key principle explaining the rapid development of the IT industry over the past half-century. What does Moore's law mean for the engineering world? First and foremost, it's about increasing transistor density. The density of transistors on semiconductor chips is increasing at a rapid rate, making more operations possible on the same size chip. Another important issue from an economic perspective is the decreasing price of electronics. As the cost per transistor has decreased, the price of electronics has continued to decrease. The last one is related to efficiency. More transistors mean higher performance, which has led to a quantum leap in the processing speed of computers and mobile devices. But it's not just performance that's increased. As the size of the direct charge has shrunk, we've been able to add circuits of different schemes, which has greatly improved power efficiency. Think about it. What if, like the Turing machine or the ENIAC, we used transistors with giant cogs that looked like light bulbs? Imagine 1 billion of them working simultaneously, and the power consumption would be staggering. If we had as many computers and wireless communications devices made of these giant components as we do today, I'm pretty sure we'd run out of oil on the planet within a week. Of course, such a thing is only possible in our imagination. But Moore's law can't hold forever, because we can't shrink the size of transistors indefinitely as we approach physical limits. Let's look at why this law is broken. There are many reasons, but here are 5. First up is the issue of size. As we covered in the quantum mechanics section, the principle of indeterminacy, the smaller the size of the device, the less accurate predictions we can make about its behavior. It's called the principle of indeterminacy. As transistor sizes get closer to the atomic level, we're running into physical limitations such as quantum effects. See the card on the right for more on this. The second problem is electromagnetism. In most countries, electromagnetism is taught in high school physics courses, and the principles are studied in depth in university majors. It's the subject that makes many students give up on physics. Well, it's still better than quantum pharmacy. Anyway, as the size of transistors gets smaller, problems like cross-interference due to electromagnetic fields arise. Let's start with the basics. The movement of electrons creates a magnetic field, and the magnetic field changes the electric field. The altered magnetic field in turn creates a force that interferes with the movement of electrons, i.e., the flow of electricity. The faster the electrons move, the stronger this opposing force becomes. This action slows down the speed of information transfer. It's not just a matter of reduced speed. Imagine we have 2 parallel wires with the electricity flowing in opposite directions. These will act to cancel each other's electromagnetic fields. This causes the strength of the electricity to weaken. As the electrical signal becomes weaker, it becomes harder for the computer to distinguish between ones and zeros. Let's look at crosstalk a bit more. Again, to summarize the phenomenon, cross-interference is a phenomenon where electromagnetic fields interact between adjacent circuits on a semiconductor chip, causing signal interference. As transistors get smaller and circuit density increases, this can cause problems. Firstly, it distorts the signal. The electromagnetic field interaction between adjacent circuits can distort the signal, which can cause errors in the data transmission process. Second, it increases power consumption. When cross-interference causes unwanted signals, additional power is required to compensate for them. This increases overall power consumption. Finally, there's the thermal issue. Dealing with signal interference generates additional heat. This reduces the performance of the chip and increases cooling costs. The heat issue just mentioned is also an important reason why Moore's law is broken. The heat generated by crosstalk is not possible for some. An even bigger problem with heat is that of space. The more transistors you cram into a smaller space, the more heat you generate, and the more you limit your performance gains. The last issue to mention is the economic cost. If you have infinite money and infinite time, you can build anything you can imagine as long as it doesn't violate the laws of physics. Question: the problem is that we have limited money and limited time. Specifically, chip manufacturing requires astronomical amounts of money. You can't compare it to software. You can't compare it to fabrication. You need a facility that can do fabrication, and you need a factory that can do it in large quantities. The process of making semiconductors, the process of making transistors from semiconductors, the process of designing and experimenting with transistors, and finally the process of mass production requires astronomical amounts of money at every stage. As technology approaches its physical limits, the cost increases exponentially. For companies, it is no longer feasible to make huge investments to follow Moore's law, because not only are the costs astronomical, but the risks are also enormous. So there you have it, an explanation of what Moore's law is and why it's broken. Next time, we're going to take a closer look at the physical limitations and what engineers are doing to overcome them. See you next time.
Subscribe it.